Prepare you a little bit for your exam, we started capacitors, and we actually did quite a deep dive into the whole point of capacitors, physically how they work, and mathematically how they are expressed. So I started off by showing you a very simple capacitor resistor circuit, right? With a battery or voltage, something, a capacitor and a resistor. So capacitors work in two ways. Some time is spent charging the capacitor. This is called the charging up period. And these are denoted, or these are expressed by these traces here. You have the current, you have the charging current, and you have the charging voltage. And the whole point of charging up the battery is so that the electric field, or the potential difference that causes this electric field, is near enough equal to the potential that the battery provides. So you charge capacitors to make them batteries. And as long as this switch is open, this capacitor will try to charge. Now, because of the physicality of it, the act of squashing electrons onto one side of the capacitor plate means that it will be harder and harder to squash future electrons onto it. That's why the voltage saturates. It doesn't go any higher because, you know, there's too much negative potential, or there's too much negative charge here that prevents the rest of the electrons from reaching. But this basically happens when the capacitor voltage is near enough equal to the battery voltage, okay? So I'm basically repeating myself in that the whole point of a capacitor is to charge it up so that it pretends to be the battery that you're using to charge it with, yeah? And as you can see, likewise, the current diminishes because there's less and less electrons that are able to both go onto the capacitor and that are pushed onto the capacitor. And I wrote a paragraph there. Now, when this switch is closed and that switch is open so that the battery is disconnected from the capacitor, the capacitor is allowed to discharge through the resistor. So discharging, opposite of charging. All of this potential that was built up during the charging period is now able to be released. And the electrons begin to just rush out and deposit their energy onto the resistor until the circuit equilibrializes. And because they can go nowhere else except through the resistor and onto the other capacitor plate. And then it gets to a point where the whole circuit is in equilibrium, nothing's happening. And you can see that, again, the initial charging, or I should call this discharging current, this in this case would be called the discharging current. Let me just correct that. So this would be called the discharging current. It's very high at the beginning. Then as there are less and less electrons on the plate to push them off, the current tapers off because there's less push now. There's less push. Both of these situations are all about pushing. There's too much push here, so the electrons find it harder to get onto the plate. That's why the charging current tapers off. In this situation, there's not enough electrons on the plate, so there's not enough push anymore. Again, the current tapers off. And the voltage tapers off as well, because as long as the circuit begins to equilibrialize, so pretty much equal numbers of electrons on both sides of the plate, there is no more electric field. There's no more potential difference across the plate. So the voltage also tapers off. The strength of a capacitor, or the strength of some electric vehicle or some electric skateboard, is how much charge or how much potential difference you can create across the plate and how long it takes to discharge. So the best electric vehicles or the best electric skateboards, scooters, whatever, have very long discharge times. It takes a very long time for the discharging current to fall to zero. And it takes a very long time for the discharging voltage to fall to zero. so that you can get a pretty much average power over a longer period of time. P equals VI, right?
Mm-hmm.
Get a very large average power over a longer period of time. So it could be that in this section here, let's say here, this was RC, so that's the time period. So I'll talk about the time period again. So that's the time period. This could be like 3 hours. This could be like 3 hours. So it takes 3 hours to drop from a very high voltage and current to maybe 70% of the original original value. And that depends on the material or the way the capacitor was made. When you make a capacitor and you want it to act like a battery, you want to make sure that your time period, the time taken to fall to a certain value of current or voltage is very long. Otherwise, it's pointless. If this happens in minutes or seconds, then it's rubbish. There's just no point. The only exception though, is in the electronics, like in your computers, your phones, basically handheld electronics, computers, because you want very fast discharge times, because you have switch circuits. There's so much going on. Maybe when I'm doing this or I'm playing a game, my graphics card, whatever, we need very quick charging and discharging periods. So the exception is that, or those situations there. Okay. Then I went on to talk about some basic equations that define the amount of charge able to be manifested inside the capacitor. And it depends on the capacitance of the capacitor. Basically, the capacitance is a function of the area of the plates and the material in between the plates. Right? So if I was to write in red, capacitance is a function of the plate geometry. So whether they're circular, whether they're square, how big they are, and the material between the plates. So sometimes the material between the plates is just air, okay? Mm-hmm. Other times the material in the plate, it's some dielectric material. It could be some very thick paste or some solid material, but it also depends on the material in between the plates. So the capacitance of a capacitor is charge divided by voltage. The higher the capacitance, then theoretically, the more charge you can hold inside the capacitor. And then the work done, or the energy built inside the capacitor from charging it, is equal to half QV. Now, if we were to draw a graph, you would see that this line here would be a constant. So it would be Q, the charge built up in a capacitor is equal to how much battery voltage you connect to it. So if you were to draw a graph of this, it would be Q on the y-axis, or V on the y-axis, and X on the Q or V on the, basically Q versus V, right? Mm-hmm. And it would be a straight line, it would be a linear proportionality, and this capacitance would be the constant. You don't change capacitance in a capacitor, you just change the capacitor. But when you're charging it or discharging it, the capacitance does not change. So this is a constant. Constant for every capacitor. And it's similar to Hooke's law. Do you remember Hooke's law?
Yeah.
Yeah. When you graph the force versus the extension, the area underneath that straight line is the work done in compressing or stretching whatever you're doing. And that would be the work done built inside the string or the spring. It's the same kind of concept here, where the area underneath this graph gives you the work done or the energy built up in charging the capacitor. And this essentially is analogous to EMF. So we use a couple of different words to describe what comes out of the battery. I like to call it battery voltage. Some people call it the potential difference from the battery. Other people call it the EMF from the battery. They all mean the same thing. But if you're charging a capacitor so that it becomes a battery, then essentially the work done in charging a capacitor is basically the EMF that you are building inside it. And that EMF will be given to the electrons to do what electrons do. Yeah.